I'd like to do one more quick example, and this is looking at the derivative of the pendulum data. So this potentially a more intuitive way to look at a pendulum is not at the angle, but the acceleration of that angle. So we can look at the derivative of the pendulum angle by specifying this d operator. So we want to take the derivative of x with respect to t, and we want to do this twice to get the second derivative. So here we have the acceleration of x, the second derivative of x with respect to t. So let's look for a ordinary differential equation for this. So we're going to look for a formula as a function of x, and also the velocity of x, which is the first derivative of x with respect to t. So here we have entered in model the second derivative as a function of x and the first derivative. So clicking off, you can see we're modeling the acceleration of x as a function of x and its velocity. So let's go ahead and click Start to start looking for the second derivative model. So what you'll notice different here when I click Start is that it brings up this window, and it needs to calculate the numerical derivative of the data. Since we don't specify the derivative already, it needs to figure out what the slope is, what the timed derivative is of our data points automatically from our angle data. So to do this, it fits a spline curve and uses generalized cross-validation to pick a smooth of our data, and that smooth is used to estimate these derivatives and propagate a new data set for us to model. So after that's done, it'll ask us would I like to resume my previous search, and no, I don't want to. I want to start a new one. So now we're going to start looking for a model of the second derivative, the acceleration of the pendulum's angle. So it looks like it found starting to find some accurate models. Let's go and look at what these look like in real time. So immediately it's picked up on this small angle approximation of a sine term. So if you know what the physics of the pendulum are, you'll remember that the acceleration is from gravity, and the gravity is dependent on the angle. So the further up the angle is, the stronger the force down is. So the small angle approximation for sine, the vertical component of gravity, is actually x. But if we give it some more time, it should pick up the trigonometric term. So looking at the most accurate term here now, you can see it's a small angle approximation component of gravity, and here we have the velocity. And so here this is a negative, so we can see this is a drag on the velocity. So the acceleration slows down more with increasing speed. Now we've picked up on the sine term, and I'm just going to let this run for a few seconds, and we'll see this prune down. Now, one thing to remember when using Eureqa is that different data sets, different problems will take different amounts of time to find accurate models. So in the examples I'm showing in this video, like before, it only took about 30 to 60 seconds to find a full model of the data. But different data sets could take several hours or overnights, depending on how complex, how many variables you're trying to model at once. So typically you want to run this overnight if you're using data that has a lot of noise in it, for example. So let's look at the most accurate model we found so far. So this looks like it's found the exact model of a pendulum. So let me just click stop here so we can look at this more carefully. So what does this say? So we're modeling the acceleration of the pendulum, and we can see here that it's picked up one component of that acceleration is this sine dependence. This would be, we can interpret this as the vertical component of gravity acting on the angle x that pulls the pendulum down, and we have this term here which is the velocity of the pendulum. So the faster the velocity is moving, the more drag there will be that acts against this. So we can see that the drag coefficient here is b is 0.75 times the velocity, and the ratio of the gravity over the length of the pendulum is 96.24. So by looking at the second derivative, we can pick up a more intuitive model here that even explains this in perhaps a more physically meaningful way in terms of the forces that act on the pendulum, the accelerations of the pendulum. So that gives you a quick rundown on how to use Eureqa. Good luck using this on your own data, and be sure to check our website for updates to the software and more help and tutorials. Thank you.